So, how to write an interpreter in OCaml. The first thing that you need to choose when writing an interpreter, no matter in which language, is what you want to interpret. Here I'm going to be using the Lambda calculus. It's a kind of programming language. It's kind of basic, but it's string complete because there is church string equivalence. So any code that you can write in any other language, you will be able to write here, maybe using different ways. So before this, please don't forget to smash that like and subscribe button and enable the notification bell. It actually matters, I know. So, okay, let's start. Here I have the project done. This code and all the tools needed are going to be on the description below. So if you want to try it on your computer, it's hopefully it's going to work. So okay, first things, I have my project working, and we need to define, when writing an interpreter, we need to define our code. Essentially our AST. Here, as we are going to be using the Lambda calculus, we have three kinds of nodes on our AST. So it's variables, abstraction, and application. Variables, they're like variables, but they don't vary, so they're more like constants. Essentially, a variable is the name of a parameter in an abstraction. So you use abstractions to create variables, and then to satisfy that variable, you use an application. And because the way that the Lambda calculus works, you can actually make these recursive without doing any magic whatsoever. So, okay, we have variable, abstraction, and application. So let's define type expression. I'm going to abbreviate it because lazy. It's going to have a string, which is the name of the variable. Here we also want its abstraction. An abstraction is a single parameter, so let's call it a string. And also, it's a single parameter, and also another expression, so the body of the abstraction. And then an application. An application is an expression, so the function to be applied on the left. And on the right, it's going to be the body. So I'm going to use, instead of using tuples, I'm going to use records. So here is the parameter. And here is the body. Same stuff here. So here is the function. I'm going to call it funct. And here is the argument of this function. So parameter is the whole on the function, and the argument is the actual thing that you throw on that function. Okay, so we have this expression. The way that I'm going to be doing here is that we have a context. So a context here, it means a map from a name, so a string, to a value. A value here is going to be a closure because that's what we have on the Lambda calculus. But essentially, you can map from an expression, from a name to an expression. That means if you have the variable x, it's going to return a value on the right. So it's actually a map. Here it's not a map to an expression. It could be, it's not. Here it's going to be a map from a string to a value. So we need to introduce the value. So the value is going to be a closure. And this closure, it's going to have, let's say, it's going to have the context, which is the context. So like it's value context t. We don't have the module context yet. And we also need the parameter name that is going to be applied, so parameter, and the body, which is an expression. So when you apply it, essentially you get this parameter, you get the argument, you add it to the context, and then you evaluate the body. So let's define the module context. Context here is going to be essentially a string map. I'm not sure if there is string.map. Yeah, no. So you can do map make string like this. And now you have this context, which is a map. And then we just need to write our interpreter now. it's kind of simple. So interpreter, I'm going to abbreviate it because I'm lazy. You should not do that in production, but I'm lazy. So you have the context, you have the expression, and then what you need to do is pattern match against the expression. And let's start with the first one. So it's a variable. If it is a variable, we are just going to do context, find a name, and then context. So that's it for a variable. If it is an abstraction, we're going to have the parameter, the body, and we are just going to return a closure. Essentially, this function, it's going to map from a context plus expression to a value. That's mostly how you define an interpreter, actually. So we have context, param, and body. And now it's where our logic actually happens. So it's an application. Application is the only thing that does anything here. So we are going to go with argument. And the first thing that I'm going to be doing is evaluating the argument. I could do in the opposite order, there is advantages, but here the code is going to be a little bit cuter if I go with argument first. So like argument is going to be an interpreter, and then I evaluate it on the current context and argument. So that's our argument. And then function, it's going to be, I'm going to make like this, interp, context, and funct. But we know this must be a closure, and we want to evaluate it. So it's context, param, and body. And then we just need to say interp with the context.add context, as I mentioned before. So we get the parameter, context, so parameter, the argument, and add it to the context. And then we run essentially the body, and that's about it. This should be Turing complete. I can try to make some recursion. If you have recursion and you have functions, actually, if you have functions, you technically should already have recursion. But essentially, with this, you should be able to describe any code whatsoever. It's great if you want to formalize the behavior of something, because essentially you have this really small subset, no mutability involved, and it's really simple to think about it. A cool property of our interpreter is that it's actually tail-call recursive. As you can see, the last call here, it's a context find, so it finishes fast, no recursion or anything like this. It's a closure, so this is essentially really fast, just a single location. And then here we end up just calling interp itself. Of course, if it's too deep, so for example, if you have a huge EST which somehow blown up, that's not going to finish. Like that may trigger call stack, like Stack Overflow, but that's probably not going to happen here. And one of the cool things I'm going to show you later is when trying infinite recursion, and that's what we are going to do here. The first thing that we need to do, the code that I'm going to be trying to write is essentially, let me get the notation. So essentially this. And it's been a long time without writing anything with a lambda calculus. So it's f, and then it's going to be ff, I think. I think that's it. Let's put some parens to ensure. So here, and then here it's going to be the same thing. So I just copy. And yeah, that should be it. So I'm passing a function that calls a function. So essentially this function is going to just call itself through the other function. So this calls f with f. And then f here is this function. So we start on this and then keep going on this second one, because yeah, that's what's going to happen. Because essentially I'm going to call this function with itself, and it's calling this function with itself again, and that's how it goes. To define it, let's define it just in a single time. So it's an abstraction of the param is I'm going to call it f, and then the body, it's going to be an application. So an application with a funct, here the funct is going to be just a variable of f, and the argument is going to be also a variable f. So here you have essentially this, and more like this. So if you have this, running the code is trivial. You can just say application of funct, which is f, and then I'm going to call f with itself. On this notation, we are essentially doing something a bit different, but here we can do this. That's actually a copy of f, so they're not the same reference or anything like this. And then we can just call interp. The context is going to be empty for us, and then the code. I could do something like this, but I know that's never going to finish. So I'm going to just say x, and let's execute it. To execute it, it should be June exec to_lang.x. Yeah, I know that it's running because I can hear my computer fun going on, like going crazy. So if you go here, you can see to_lang, it's using 100% of a single CPU, and the memory usage is negligible at best. Essentially, no memory usage. OCaml is pretty good at memory, so yeah, you can do this. Okay, let's do a small extension of it. Let's introduce the concept of native functions. Here they are going to be more like native closures, and the advantage of a native closure is that you can do anything. Like, it's going to be defined in terms of OCaml, and then you can do, for example, I/O or anything like this, and then you can start coding on your Lambda calculus. So first things, let's define a new kind of value, which is a native closure. I'm going to just call it a native, and the native is going to be essentially a value to a value. That's about it. So it's a value to a value, and now OCaml is going to be complaining to us. Oh, yeah, as you can see, it's complaining to us because this example is not handled. So let's change the code a bit. Here it's going to be this with, and then here we can do like this, and that should be. So this is essentially the code as before, and now I'm going to have value of f, and then I'm going to call it native. Essentially, is it native? Yeah. So it should be f of f. Maybe I'm losing something here. F of argument. So yeah, that should be about it. Am I doing something wrong? Oh. And now a good example of this, let's make a native function called print hello world. I'm going to add it to the context. So let's make initial context as context.empty, context.add, print hello world. This function is going to be an identity function, but it's also going to print for us. So it's going to be recursive, and it's going to print hello world and return the input. To do this, we need to do native, and here it's going to be fun v. I'm going to say print endline hello world, and then v, like so. So yeah, you can see that's the hello world function added there. It gets v and returns v, and now we have our initial context, which has this function, but our code is not calling it. To do it, I'm actually going to call, if I recall correctly, I think I should go and do application of, yeah, I'm going to apply it with the variable f, and then, yeah, so I could do on the other side, it's cuter. So like application, funct, and that's going to be our funct, so it's a variable like this. And that's our second argument here. And I think that's about it. Let's see. So what is going to happen? Yay! It's printing hello world until the end of the universe. Probably, I'm not sure, probably I'm not going to have energy at that point. But as you can see, it's printing hello world like crazy. Why is this still incomplete? There is a great video on Computer File on how how to do Boolean, essentially how to do logic using functions. I'm going to leave it linked, I think, probably around here, somewhere. In the card above, you know the stuff. It's a great video. It explains how you can do Boolean logic. So essentially you can do branching, and you can do iteration. So as you can see, it's iterating. So you can have finite recursion, you can have infinite recursion, you can encode numbers, because that's something. There is, it's called church encoding, which is really old way of encoding numbers, numbers, pairs, list, and etc. into the classic untyped lambda calculus. And yeah, that was about it. Please don't forget to smash the like button, subscribe, enable the notifications, share with your friends. Let's say graph. Yeah, that was it. Thank you. Have a nice day.